So today we will be showing you all these electrical terms: transformers, insulators, and substations. These are the basic things in electrical transmission things.
How you get the power to your house.
Yeah. Okay, so first we're going to be talking about transformers. This is an example of a pole-mounted transformer right here. It says pole-mounted distribution transformer with center-tapped secondary winding used to provide split-phase power for residential and light commercial service. This means it's like your normal neighborhood transformer that runs across your neighborhood if you live in a fairly old part of the neighborhood. No offense.
And then on newer homes, it's done underground, but it's just, you still need a secondary transformer like this. Now, here's a question. It says split phase. What does that mean? Do homes get two voltages?
Yeah.
How does that work?
It takes 120 and 240.
Right. There's two circuits with 120, and they can be combined to make 240.
Oh, okay, cool. So later, here we have a example of a substation transformer. This is used to convert high voltage into medium voltage for distribution to residential and light commercial service power lines.
So what's the relationship between that type of transformer and the one we just saw?
So this transformer connects to this pole-mounted transformer.
Right. The substation transformer, it talks to or connects to transmission lines that are very high voltage that run between towns or for large distances, and then it converts it to a medium voltage that is suitable for this pole mounted, and then the pole mounted converts the medium to residential like we have in homes.
Cool. So you might be wondering, well, how do transformers exactly work? So here's a model of a transformer here. It says ideal transformer connected with source VP, which is right here.
Primary voltage.
Yeah. And impedance on ZL, which is right here. Secondary output VS, which is right there.
Right. So we don't want it, so the VS is the secondary voltage, and then the impedance is the load or whatever resistance is on that line. Okay, what's a transformer made of?
Metal?
Yeah, iron core.
Yeah.
And usually copper wire windings.
Okay.
Now, when the current goes through the copper wire, it creates a magnetic field. Magnetic field is then creates voltage on the other winding.
Okay.
And finally, notice that it has A:1, and then they show right below it NP:NS. That means number of windings on the primary compared to the number of windings on the secondary. If the number of windings are the same, is the voltage the same?
Yes.
Yes.
Okay, so this is an example of a step-down transformer, and it has fewer windings on the secondary, which is right there, resulting in a lower voltage and higher current.
And the reason why we say that is because we don't lose power in a transformer if we can help it. Now, there's a slight power loss that happens due to inefficiency, but when the power comes in, power is measured by taking voltage times the current. So there's a certain voltage times current power coming in, and if the voltage is lower coming out, for us not to lose power, the current must be higher.
Yeah. Okay, now we're going to talk about insulators. These things you might see on a power line that runs across somewhere, So an electrical insulator is a material whose internal electric charges do not flow freely and therefore make it nearly impossible to conduct an electric current under the influence of an electric field. So note that these insulators are not perfect because a perfect insulator does not exist, because even insulators contain small numbers of mobile charges.
Now, why are they shaped the way they are?
Well, why they're shaped in a disc is to get the most surface area they can.
Right, and that's because some current will flow over the surface of the insulator, and especially on a wet day, so that's why they try to increase the surface so to minimize that loss. Now, why do they need insulators? Why not just have the wires run to the pole?
Well, because insulators are used for two main things. One, for support for the wire coming into the pole, and you don't want the power to jump from the pole to the ground and short out,
Yes.
or like
We would lose
cause.
all the power at the first pole it hit because they're all made of metal.
Yeah.
Or even wood can conduct. So we would lose all our power if we didn't use insulators because it would go right through the pole down into the ground.
So you may be asking, well, why are insulators mainly made out of plastic or glass?
Ceramic, yeah.
Or ceramic. Well, that's because glass flows freely, but electrons don't, because
Light, you're saying light does.
Yeah, light.
Yeah, that's a special property. It's an interesting observation that there's a direct or there's an inverse proportional that the amount of light that goes through an object, it's usually an indication of how conductive or not it is. If light can go, if this object is transparent or translucent, that means it's probably a good insulator.
Yeah, and well,
So glass kind of tells us, even if we didn't know if glass was, we would have a suspicion that we would want to use it for insulation because it's transparent.
Yeah, so this is not one that we put in this one, but a conductor is an opposite of an insulator.
Yes.
So.
And usually made of metal.
Yeah.
Is metal a good insulator? No, it's a conductor, and light doesn't go through it, it bounces off it. That's why mirrors are made with metal.
Okay, now the final thing we're going to be talking about, substations. There's two substations, well, there's more, but two that we're going to be talking about today. So, first is called a transmission substation. A transmission substation connects two or more transmission lines or power lines. Such substations contain high voltage switches that allow lines to be connected or isolated, which is another word for disconnected, for fault clearance or maintenance. This means if a tree falls down on the line, then you can switch it off immediately.
And that doesn't help the people with the tree on their line, but it does help the people that are on the other side, on the other substation, that can get it switched off so they keep their power.
Yeah. Okay. And finally, a distribution substation. This, how it works is it transfers power from the transmission system to the distribution system of an area. Transmission voltages range from 115 kilovolts to 765 kilovolts alternating current, or in other words, 115,000 volts to 765,000 volts, and distribution voltages range from 2.4 kilovolts to 33 kilovolts.
And these voltages are all very dangerous, so we wouldn't want to fly a kite around them or get near them because we could get injured very quickly.
Exactly, because, you don't want to mess around with them. Okay, thanks for watching. Here's the credits for this slideshow. It's Wikipedia, my dad, of course, and Google Images.